Okay, so this is experiment 3, acceleration along a ramp. And what I have here is an air track. This is a very low friction apparatus, and you have a little cart that can move along the track. This is a blower, so it's like using a vacuum cleaner in reverse. You're using that air that's coming out of the blower, and it goes into the track, and there's some little tiny holes here that allow the air to come out. And the cart will float on this air. So let me show you that. If I turn it on, maybe you can see the cart move just a little bit, and if I give it just a little tiny push, it moves along. Okay, very low friction. So also on the track, we have photo gates. So what these photo gates will allow us to do is they will allow us to see how long the cart spent in the gate. We're going to measure, or I'm going to give you a measurement for the length of the cart. And by knowing how long the cart was in the gate, that length of the cart divided by the time in gate gives you the velocity in that gate. Now, if the air track is horizontal, I shouldn't expect to get any acceleration. If you're horizontal, the acceleration is equal to 0. If you're vertical, the acceleration is equal to g. And everything in between goes like, well, we'll leave that for later. All right. So let me show you a little bit about the software. If we can zoom in on that. Okay. So here is the flag length. That's the length of the cart, which I'll give you. Here is the photo gate spacing. That's the distance between the photo gates. So we really don't need that for what we're doing. Well, okay. We're going to have the velocity in the first gate and the velocity in the second gate, and then by knowing the time between the gates, we'll look at the difference in velocities and the time between the gates, divide, and that will be the acceleration. Okay? Now, you would expect, like I just mentioned, that on a horizontal track, the acceleration should be equal to 0. So here's the Excel spreadsheet that the computer will fill out when we actually do the experiment. So this is time in gate, time between the gates, and velocity in gate. So let me go ahead and see if I can do one run horizontally just to show you how the software is going to work. So I'll press start, and I'll give the cart a little push. That was the first gate, that's the second gate. So now here's the first gate. That gives you the time in the first gate. There's the time in the second gate. There's the time between the gates. And here's the one we're looking for, the velocity in gate. And you can see that there's a little bit of difference between these two velocities. The velocity in gate 1 was 0.3259 meters per second, and the velocity in gate 2 was 0.3262. So very, very small. So by knowing the difference in these velocities, that's delta V, and the time between the gates, we can calculate the acceleration. And we would get a very, very small acceleration. So in the next segment, what we'll do is we'll raise the ramp and we'll do some runs uphill and downhill. Okay, so now I've placed some blocks underneath the ramp to give it a slight angle. So what we're going to do is we're going to calculate the acceleration or measure the acceleration for this angle. And one of the things that we need to know first off for comparison is the angle itself. And so on the ramp or on the board that the ramp is sitting on, there's a mark here. It's difficult to see, but there's a mark here, and I'm going to measure the distance from the bottom of the board to the top of the table. That makes an angle with the table. This would be the hypotenuse along the board. This would be the base, and then the height that I measure is, let's see what I get. So I'm going to put this at the 100 centimeter mark on the hypotenuse, and I get 7 centimeters. So let's walk over to the board and I'll show you how to calculate what we're going to use to calculate that angle. So, you know from trig, for a triangle, the height for a right triangle, this is a right triangle. For the height over the hypotenuse, that's equal to sine theta. So that's what I've written here. Sine theta is equal to h over 100. Because the hypotenuse length was 100, and that's h that I just measured. So theta is equal to the inverse sine of h over 100. Here's the calculation. It's 7 over 100. Units cancel out. Inverse sine, and you get something that's about 4 degrees. Okay, now you may think by looking at this that, wow, that's a big angle. But actually it's only about 4 degrees. And if you think about your little 8.5 by 11 piece of paper that you typically draw angles on, you're only drawing maybe about that much of the angle. So you can see that it's a very small angle, okay? So now what we're going to do is I'm going to crank up the air track and I'm going to let the puck go downhill. All right. The software is going to measure the velocity in gate 1. The velocity in gate 2 should be speeding up, and the time between the gates. And the difference in those velocities divided by the time between the gates is the acceleration. Then I'm going to do a run uphill. So I'll try very carefully to push the cart uphill. I want to make sure that when I push the cart, I'm not pushing the cart when it's in the gate, okay? Because that would mean that I'm applying a force to the cart and accelerating the cart while it's in the gate. I want it to be just the acceleration due to gravity along the ramp that's being measured. Now, question. Should the acceleration uphill be the same as the acceleration downhill, magnitude-wise? The answer is yes. In a perfect world, they should be the same. In one direction, it's slowing down. In the other direction, it's speeding up. But that acceleration vector is this way along the ramp. Okay, so let's try a downhill run. All right, so I'm going to start, and here we go. Okay. So if you can bring the camera over here and take a look. There's the velocity in gate 1, the velocity in gate 2, and you can see that it's sped up considerably. It's almost double what it was in gate 1, in gate 2, and the time between the gates was about a second, okay? So the difference in these velocities divided by the time between the gates is the acceleration downhill. Now, I'm not worried about the SIGN of the acceleration. We're just calculating the magnitudes. We understand that if we define a direction for the acceleration, say positive is uphill, then we have a negative acceleration going downhill, but I'm not worried about that. Okay, so let's try a run going uphill. So I'll stop this and clear the data. Okay. Now I can tell you an uphill is a little bit more difficult because you have to push it hard enough to get completely through this second gate, and also I need to catch it when it comes up here. I don't have to catch it, but it makes the data set a little bit easier to work with, so here I go. Not bad. Okay, so here you can see that in the first gate, it was going 1.7784. In the second gate, 1.2316. So it slowed down quite a bit. And I gave it a pretty good push. So the time between the gates is 0.6815 seconds. So once again, by looking at the difference between the velocities in the gates divided by the time between the gates, you'll be able to calculate that acceleration uphill.